last class we looked at some circuit implementations of latches and flops, right? And we could broadly classify them into two kinds, right? So we had one like this, right? Let me call this phi bar, and phi clock, right? So this was my D, this was my Q. Then alternately we said we could have another implementation of such a flop, of such a latch, right, which is like this. So we can retain this pass transistor phi, but remove this, TG1, TG2. We can remove TG2, right? So this was basically called breaking the feedback path. And this was, last time I said it was not breaking the feedback path, it's better known as overpowering. Overpowering feedback, right? And here the key advantage we said was transistor sizes don't matter for functionality. Right? Here transistor sizes matter, right? So this is I1, I2 and I3. I1 comma I2 should be much greater than I3. Okay, because there will be the node X will be in contention between I1 and I3 when you're trying to overwrite a data, right? This is DQ, right? So if you want the node X to flip, then I1 must win under all process conditions, and therefore I1 must be much larger than I3, right? The reason I'm saying I2 must also be larger is when I cascade these latches and make a flop, then I2 becomes like I1 for the next stage, right? So you need that actually not true, because there is an I1 there which is available to overpower it. But if you don't put that I1 in between there, then you might have to, for example, there is an inverter here, then the next stage you could choose to skip I1 sometimes, okay, if you're okay with that inversion, in which case you should make sure that I2 is also larger, okay. Otherwise I would say this is not absolutely necessary. Okay, this is where we stopped last time, and we had made some assumptions about the clock. Okay, one, it is ideal edges, right, which means rise / fall time equal to 0 in our analysis till now. Then we also made another assumption that clock, right, or phi as shown here, and clock bar, that is phi bar, have no skew. What is skew? It means the edges are perfectly aligned, right? This is the assumption that we made, and based on that we got some analysis, we got some expressions for the setup time and the clock to queue delay and the hold time and all that, and we found that the hold time was basically what? Negative or zero essentially, because we said that the clock is instantaneously shutting off. Okay, so now we will look at a simple example to understand what happens if this assumption does not hold. Okay, so if clock and clock bar have overlap or delay. Okay, what does this mean? So I am still assuming that the edges are still perfect. Instantaneous rise, instantaneous fall. Okay, that we are not removing for now. This is my clock. Clock bar should have ideally been like what? It should have been like this. It should have ideally been like this. Right? But now I am saying that this edge is moving and it is, let's say, moving to the right. Okay? Clock bar is moving to the right. So remember, all our definitions of setup, hold time, everything is with respect to the clock, not clock bar. By definition, it is with respect to CLK, not CLK bar. So therefore, I am going to move clock bar around that edge. Okay, so let's assume that this moves like this. I'll draw it slightly exaggerated. Right, so what happens in this period? This is a period of 1-1 overlap. Ideally, these two clocks should have had no overlap. That means clock and clock bar cannot be equal at any instant of time. But now there is a 1-1 overlap in that region, and in this region here there is a 0-0 overlap. Okay, so what we want to do is we want to see what happens because of this to the, let's say, the hold time. The hold time was 0, right? We want to see if that is going to change. So for that we will consider a rather simple example, okay, where I am going to remove the PMOS transistors from my transmission gates from the previous circuit. Okay, so I basically have this. Okay, size doesn't matter now. Okay, this is clock bar, clock bar, so this is QM, Q, right? So, and what is this? This is clock, by the way. Okay, first of all, latch L1 and latch L2. Latch L1, is it a negative latch or a positive latch? It's a negative latch because so is L1 a negative latch or a positive latch? So positive latch, because when clock is 1, data is shooting through the thing and getting to the output, right? This is my D. So therefore this is a positive latch and L2 is a negative latch. So therefore this is a negative edge triggered flip flop. Okay, so together you get a negative edge flop. Okay, so now I want to impose this condition that I just told you, where I have a 0-0 overlap and a 1-1 overlap. Okay, so first of all, what is the expected behavior? Okay, let me maybe I'll just remove this. I can use this space well. Okay, so I have my data D, and this D as usual is making some transitions here. So this is D1, D2, D3 and D4, and it eventually go to D5. Okay, what is the expected output on Q? What is the expected? Which data should it sample? Huh? This is a negative edged flip flop, right? And therefore it is going to sample which data? It's going to sample D3 and it has to hold it, right? And yeah, okay, and the change in D2, what should happen to that when it goes to D2, from D2 to D3? I'm sorry. What should happen to that? What is shown in the arrow here is the sampling edge. Correct. At sampling edge, it should sample. What should happen if the data changes on the non-sampling edge? Should be ignored, right? Data should not go through. That's the intent. So that's what we want to see, and we want to understand what happens here. Okay. So let us look at the case when my data changes out here, which is what? What is this overlap? One overlap. So if both clock and clock bar are 1, it means that both these pass transistors will be on, right? And of course, even these transistors are going to be on now for a short period, right? So any change in my data D, right, like shown here, when it goes to D2, right, at the non-sampling edge, can actually race through from the input to the output, because there is a path available here like this. Okay. Now let's put down what should happen after the overlap period in both cases. Okay. What should happen here, for example? In this period, what should the state of L1 and L2 be in terms of transparent or opaque? Clock is 1, transparent, L2, opaque. Similarly, I have something here, right? L1 is what? Opaque, and L2 is transparent. Correct? So now my question is, there is an overlap, okay, and data can potentially shoot through, right? But question is, does the data always reach Q? Always. Is there some delay constraint that I can impose so that it doesn't reach Q? That's all I need. My flop behavior is data is changing on the non-sampling edge, that should not appear at the output queue. That's all. It can affect any internal node, right? So you see what happens after this particular period here, right? In the sense, L1 is going to become transparent after the 1-1 overlap, correct? And L2 will become opaque, which means it's going to hold the data. So suppose the data actually crossed this flop here. If the data came all the way till here, then you are done. It is going to sample that and will hold it through the rest of the period, right? So therefore, I cannot allow my data to shoot through till here, but I can allow it to shoot through till here, correct? Let me, yeah. Because after my clock bar goes low, it is going to shut off that thing. So as long as that feedback loop is not affected, I don't have a problem, right? So what is the delay constraint in relation to this overlap period that I can impose? Basically what I am asking is, what is the maximum 1-1 overlap that I can tolerate so that this flop does not misbehave? So you said 2 inverters. So let us now label them I1, I2, I3, I4, I5 and I6. Then I have N1, N2, N3 and N4. Yeah. So what is my condition? T overlap 1, 1. So it should be Ti1 plus Tn1 plus Ti2 plus I4. Yeah, right? If I can ensure that it goes only this far, there's no problem. So what should be the inequality between the left and right hand side? T overlap 1, 1 should be lesser than this. If I ensure this, then there is no problem. Okay. Remember, now this overlap condition is a little complicated in the sense that if there is a violation, then my flop is gone. So it is your job as a designer to ensure that there is sufficient delay from the input to the output so that you don't have this race condition. Okay. Now, yeah. Correct. No, but how will it cross I2 and I4 without crossing I1 and N1? No, be careful. This is the non-sampling edge. This is not the sampling edge. The sampling edge, I agree with you. Setup time would have ensured that data is stable. Then data has to go past only that from, I2 to I4. This is the non-sampling edge. So data should not even enter actually. Be careful about that. That's the whole point, right? So here, this is the non-sampling edge. Okay. Okay, so you have to. So now you think about it. Suppose I design a flop without this I1 and I4. It's possible, right? I mean, data will be inverted. D and QM might be inverted, but that's okay. I can always have some flop like that, right? Then remember that you are actually reducing this delay that is available to you. If I have more inverters on the path, then I can tolerate more clock overlap, right? If you reduce that, then you are running into the risk of reducing that overlap time, and you have an issue there. You have to be very careful about that. Okay, so that's so this is called a race condition. Okay, now what happens on the zero? Yeah. No, what is T? N2 or N3? N3. So what happens? See, the thing is, this guy is in the, there is a feedback inverter on the other side. Now, if this in capacitor after N3 charges slightly above the trip point, then that feedback inverter is just going to hold that value forever. So to be careful, it is better to cut it off before. Yeah, that's all. You can be sure if you impose this condition here. That's all. Beyond that, there is a risk. Okay, you can tell the designer, you can tell the consumer of this flop that look, don't go beyond this overlap time. For sure, it will work. But beyond that, there is a risk. But in reality, you're right. There is, as I told you, the edges are not ideal, and all of this is not ideal, right? In that case, the number will be in between considering N3 and not considering N3. Okay. Now, what happens in the 0-0 overlap case? Suppose what happens first of all to the NMOS transistors when there is a 0-0 overlap? All of them are off, which means that there is no path available from D to Q. Forget D to Q, even from D to QM, there is no path. And therefore, you really don't have a problem in this flop, right? T overlap 0-0, no problem. Yeah. Where? Correct. Correct. Now, if D changes, no, you are talking about this transition, right? What I marked here. D3 to D4. Correct? That's the sampling edge. You are talking about that transition. But I don't want D4 to go through. I want D3 to go through. D3 has changed setup time before the sampling edge. And that is what should go out to the end. Not D4. The moment, that's why I'm saying everything is the reference to the clock, not clock bar. After that clock bar sampling edge, I mean after the clock sampling edge, any change should be ignored. Okay? Right? No. In this configuration, there is no problem. Because the moment I go past the sampling edge, all my NMOS transistors are off. Feedback path and direct conduction path. Yeah. No. First of all, data changing at the negative edge has no meaning here because it's an instantaneous thing. Right? So it changes, let's say, just after. That there's no problem. I'm saying under the assumption that the clock edges are instantaneous, all clocks turn off. And therefore, there is no way D can enter QM. Forget Q. Wait, I know. I'll come to that. That's not in this configuration. Okay, I totally understand what you're saying, but in this configuration, it doesn't hold. Okay, so let's now answer his question. Yeah. when we talk about these overlaps and all this, it cannot be a significant fraction of the clock period. By definition, these overlaps are very small delays. Otherwise, you have a problem in the system, right? Clock overlap, jitter, skew, all of these things are very small numbers compared to the clock period. Otherwise, your system is not going to function anyway. Okay, that's a corner case that we don't have to worry about. Okay, so let us now, so what is so magical about this flop, right? The 0, 0 overlap, there is no issue. How come? So what other configuration do you think will have a problem in the 0, 0 overlap? All I have to do is put a PMOS transistor in here, right? Here and here and all that, and have these transistors conduct even in the 0, 0 case. That's all, right? With the other PMOS ends connected to the appropriate clock polarities. Clearly, if clock and clock bar are now 0, 0, then instead of the NMOS, all the PMOS transistors will be turned on. And therefore, this is a condition which is very identical to what we saw earlier on the non-sampling edge, where there was a race through condition possible. That means the change after D3, right, which is basically this guy, this change after the sampling edge D3 to D4 can potentially race through. Okay, now you have to carefully see what happens. How much of delay can we tolerate there? Let us say, right, like the last time, I'm trying to see if there's a condition like this that we can arrive at. Let us say that the data just got past this transmission gate into this node X. Let's say it just got in there. Okay. In what mode is L1 after that, after the overlap period? Yeah, L1 is opaque, right, which means that this feedback path is going to hold that value. What happens to L2? It is transparent. So if the data sneaks past that transmission gate and just gets to node X, data will get sampled all the way to Q and you're gone. So I can literally tolerate no delay in this case. So what I'm asking is, like the last time, we said that, you know, the data can come all the way till here, but not till here. And we impose some condition for the overlap time. Is there a similar condition I can impose here is what I am asking. For that, you have to analyze and see what happens after the overlap period. Okay, so this is my 0, 0 overlap period that I am considering. What is the state of L1 and L2 after overlap? L1 is becoming opaque, L2 is becoming transparent. Therefore, if the data gets to node X, if the change in D affects node X, right, that is X now becomes D4, then data can go through all the way to Q, because after my overlap period, this feedback path is going to hold that value. The L2 is now going to be transparent. Therefore, data can go through all the way after the overlap period. And therefore, I can tolerate no delay actually in this case. I cannot, by putting more inverters, nothing, I can handle that kind of a delay. Data should not go past that transmission gate. So how do you handle it? If I put a PMOS, no, same thing. I'm saying you connect this polarity to clock bar and this to clock, right? And this again to clock bar. No polarity change. I'm just making a pass transistor into a transmission gate. That's all, right? So what do I do? At least earlier I had a couple of inverters and pass transistors where I could absorb that delay. And so if I wanted, for example, more delay to handle a larger overlap, I have to maybe add more inverters in this part. for the 1-1 overlap, right? What do I do in 0-0 overlap? No. So again, for this configuration, what do I do? Because whether it's NMOS or transmission gate, that comes from a different consideration, whether that's an acceptable flop or not, right? It has its limitations and cannot be used everywhere. So in general, what do you do? So that's where this hold condition comes in. I can tell the consumer of this flop that, look, you need to hold the data after my sampling edge at least for some time. What is that time? It is this clock overlap time. If you tell the consumer that if you change the data before this hold violation, hold time, then I cannot guarantee that the flop will work correctly. So this, you basically say, impose it through the hold time, and what should be hold time should basically be greater than T overlap of 0, 0. So if you impose a condition which is larger than the worst case overlap of 0, 0 that you will see, then the consumer of this flop, this becomes an invalid condition, invalid use case. Hence, I don't have to worry. That's the consumer's problem. Okay? Any questions here? Yes. Yes. This is the minimum hold time that you will see in a flop, and the hold time origin is basically clock overlap. Okay?